Right now, approximately 26,000 light-years from where you're sitting. Something so massive and dense that it warps space and time into an inescapable gravitational trap is quietly devouring everything that comes too close. Sagittarius A*, the supermassive black hole at the center of our galaxy, contains the mass of 4 million suns compressed into a region smaller than our solar system. Its gravitational field is so intense that space itself becomes a waterfall flowing inward faster than light can swim upstream. We've always thought of black holes as cosmic vacuum cleaners, ultimate destroyers that consume matter and energy, crushing everything that falls past their event horizons into an infinitely dense point where the laws of physics break down completely. Death traps scattered throughout the universe like gravitational landmines, marking the spots where space and time collapse into mathematical singularities that physics cannot describe. We were completely wrong. What if I told you that black holes might not be destroyers, but creators? That these cosmic monsters we've feared as the ultimate expression of gravitational violence might actually be doorways. Gateways connecting our universe to other universes, other realities, other dimensions of existence that lie beyond our current understanding. The mathematics of general relativity, combined with cutting-edge quantum theory, suggests something so extraordinary it challenges our most basic assumptions about the nature of reality itself. Black holes might be cosmic wormholes. Every time matter disappears past an event horizon, it might not be destroyed, it might be traveling to another universe entirely. The information paradox that has puzzled physicists for decades. The mystery of what happens to information that falls into black holes might be solved by recognizing that nothing truly disappears. Instead, it emerges somewhere else in another cosmos through the quantum gravitational machinery that transforms black holes from cosmic graveyards into cosmic birth canals. The theoretical foundation for this revolutionary understanding comes from the deepest mathematics of space and time. Einstein's field equations, when solved for extremely massive rotating objects, don't just predict the existence of black holes. They predict the existence of passages through spacetime itself. What we call the Einstein-Rosen bridge, more commonly known as a wormhole, represents a legitimate solution to the equations that govern cosmic structure. Recent theoretical work by physicists like Juan Maldacena and Leonard Susskind has demonstrated that quantum entanglement, the mysterious connection between particles that Einstein called spooky action at a distance, might be mathematically equivalent to the geometry of wormholes. Their ER EPR conjecture suggests that every pair of entangled particles is connected by a microscopic wormhole, and that larger wormholes might emerge from the collective entanglement of massive numbers of particles. But here's where this becomes personally profound. If black holes are indeed gateways to other universes, then the cosmos is not one isolated reality, but an infinite network of connected realities. Every black hole in our universe might lead to a different universe, and every black hole in those universes might lead to still other realities, creating an endless web of interconnected cosmic domains. Think about what this means. The supermassive black hole at the center of our galaxy might be a portal to a universe where the laws of physics are subtly different, where matter organizes itself into structures we can't imagine, where consciousness might evolve along paths completely foreign to our experience. The stellar mass black holes scattered throughout our galaxy might each represent doorways to pocket universes. Baby cosmos that began when massive stars collapsed and their matter emerged as the Big Bang of new realities. And if matter can travel through these cosmic gateways, what about information? What about consciousness itself? The implications ripple through every aspect of our understanding of life, death, and the ultimate fate of awareness in the universe. The observational evidence supporting this radical reinterpretation of black holes comes from the most sophisticated instruments humanity has ever built. The Event Horizon Telescope has given us the first direct images of black hole event horizons. revealing structure and dynamics that don't match the simple point of no-return models we've relied on for decades. The LIGO gravitational wave detectors have observed black hole mergers that release more energy and gravitational waves than all the stars in the observable universe combined. Energy that might be powering the creation of new cosmic domains on the other side of spacetime. Even more remarkably, recent analysis of Hawking radiation, the thermal emission predicted to emerge from black hole event horizons, suggests that this radiation carries encoded information about everything that has fallen into the black hole. If this information is preserved and transmitted, it might be emerging in other universes as the fundamental data that defines the structure and evolution of those realities. Tonight, we're going to journey through the most mind-bending possibilities that modern physics has revealed about the true nature of black holes. We'll discover how quantum mechanics and general relativity combine to suggest that space itself might be woven from quantum entanglement, how black holes might serve as cosmic recycling centers that transform matter from one universe into the building blocks of another, and how consciousness itself might persist across these interdimensional transitions. We'll explore the mathematics that transform black holes from singularities of destruction into passages of creation, the observational evidence that suggests our universe might be just one node in an infinite network of connected realities, and the profound implications for what it means to exist within a cosmos that extends far beyond the boundaries of our observable universe. You'll understand why leading theoretical physicists now consider wormholes not just possible, but probable, why the information paradox that has puzzled quantum theory for 50 years might be solved by recognizing that black holes are cosmic doorways, and why your own consciousness might have connections to awareness in other universes through the quantum entanglement that links all matter across interdimensional space. If you're fascinated by the possibility that black holes might be cosmic portals rather than cosmic prisons, that our universe might be connected to infinite other realities through gravitational gateways scattered throughout space, subscribe and hit thumbs up. And here is a question that will take on new meaning as we explore these cosmic possibilities. If you could travel through a black hole to another universe, knowing you could never return, what would you hope to find on the other side? Comment below. I'll pin the most imaginative answer, because the universe might be far stranger and more wonderful than we've ever dared to imagine. But we're getting ahead of ourselves. To understand how black holes might serve as cosmic gateways, we first need to understand what black holes actually are at the deepest level. Not just massive objects that curve spacetime, but dynamic structures where the fabric of reality itself becomes so twisted that it might tear open passages to other dimensions entirely. Now let's begin this journey into the heart of cosmic darkness, where the ultimate mystery of gravity might reveal the ultimate connection between all possible universes. Chapter 1. Beyond the event horizon. To understand how black holes might serve as gateways to other universes, we must first journey to the most extreme environments in the cosmos, regions where space and time become so distorted that our ordinary understanding of reality breaks down completely. The event horizon of a black hole represents more than just a boundary beyond which escape becomes impossible. It represents the threshold where physics as we know it transitions into physics as we've never imagined. The formation of a black hole begins with the death of a massive star, at least 25 times more massive than our Sun. When such a star exhausts its nuclear fuel, the outward pressure from fusion reactions can no longer balance the inward pull of gravity. In less than a second, the star's core collapses from a sphere larger than Earth to a point of infinite density and zero volume, what physicists call a gravitational singularity. But recent theoretical developments suggest that this simple picture of collapse into a singularity might be fundamentally incomplete. The mathematics that describe black hole formation, when combined with quantum mechanical principles, reveal possibilities that transform our understanding of what happens when matter falls past the point of no return. The event horizon itself, traditionally understood as a one-way membrane surrounding the singularity, might be far more dynamic than previously imagined. According to general relativity, the event horizon forms at a specific radius called the Schwarzschild radius, where the escape velocity equals the speed of light. For a black hole with the mass of our Sun, this critical radius is approximately 3 kilometers. For Sagittarius A*, the supermassive black hole at our galaxy's center, the event horizon has a radius of about 12 million kilometers. But Einstein's equations reveal something extraordinary about the geometry of space and time near the event horizon. As an outside observer watches matter fall toward a black hole, something remarkable happens. Time dilation becomes so extreme that the infalling matter appears to slow down, redshift, and fade from view as it approaches the horizon. From the perspective of the outside universe, matter never actually crosses the event horizon. It appears frozen at the boundary, its light redshifting to infinity. However, from the perspective of the infalling matter, the journey continues normally. The traveler passes through the event horizon in finite time, experiencing no special boundary or barrier. This paradox, matter simultaneously frozen at the horizon and passing through it, suggests that the event horizon might not be a simple boundary, but a complex interface between different regions of spacetime. Recent work by theoretical physicists, including Susskind and Maldacena, has proposed that this paradox resolves through quantum entanglement. The matter that appears frozen at the horizon from an outside perspective might be quantum mechanically connected to matter emerging in another region of spacetime. The event horizon becomes not a wall, but a portal, a quantum gateway where information and matter transition from one cosmic domain to another. The mathematical framework supporting this interpretation comes from string theory and the holographic principle. These advanced theoretical frameworks suggest that all the information contained within a black hole might be encoded on its two-dimensional surface, the event horizon itself. This holographic encoding could explain how information passes through black holes without being destroyed, preserved in the quantum structure of the horizon and transmitted to connected regions of spacetime. Stephen Hawking's discovery that black holes emit thermal radiation added another layer of complexity to black hole physics. Hawking radiation arises from quantum fluctuations near the event horizon, where virtual particle pairs are created and separated by the intense gravitational field. One particle falls into the black hole while the other escapes as thermal radiation. Over immense timescales, far longer than the current age of the universe for stellar mass black holes, this radiation causes black holes to evaporate completely. But Hawking radiation creates a profound paradox. If black holes evaporate through thermal emission that carries no information about what fell into them, then information would be destroyed when black holes evaporate. This violates a fundamental principle of quantum mechanics that information must be conserved. The resolution of this information paradox might lie in recognizing that black holes do undestroy information. They transmit it through space-time to other cosmic regions. The interior geometry of black holes, as described by the complete Einstein field equations, reveals even more extraordinary possibilities. Beyond the event horizon, space and time exchange roles in a precise mathematical sense. What we experience as spatial directions become time-like, while time becomes a spatial dimension. This geometric transformation suggests that the interior of a black hole might not be a region of space at all, but a passage through time to another domain of space-time. The Kerr solution to Einstein's equations, which describes rotating black holes, predicts the existence of additional horizons and geometric structures beyond the simple Schwarzschild black hole. Rotating black holes possess an inner horizon called the Cauchy horizon, beyond which the geometry of spacetime becomes mathematically ambiguous. Some solutions suggest that this inner region might connect to other asymptotic regions, effectively other universes accessible through the black hole's interior. Even more remarkably, the complete mathematical description of black hole interiors includes regions called Einstein-Rosen bridges, geometric structures that connect two separate regions of spacetime through a throat or tunnel. While these wormhole solutions were originally considered purely theoretical, recent work in quantum gravity suggests they might be physical realities created by the quantum entanglement between matter falling into black holes and matter in other cosmic regions. The observational evidence supporting these radical reinterpretations comes from cutting-edge astronomical instruments. The Event Horizon Telescope's images of the supermassive black holes in M87 and Sagittarius A** reveal event horizon structures that are more complex and dynamic than predicted by simple models. The observed rotation patterns, magnetic field configurations, and matter flow around these black holes suggest complex interior geometries that might support traversable pathways through spacetime. Gravitational wave astronomy has added another dimension to our understanding of black hole dynamics. The LIGO and Virgo detectors have observed dozens of black hole mergers, revealing that these collisions release tremendous amounts of energy as gravitational waves. The efficiency of energy release in these mergers, sometimes exceeding 5% of the total mass energy, suggests that black holes possess complex internal structures capable of storing and releasing rotational energy. More intriguingly, some gravitational wave signals show unexpected features that might indicate the existence of echoes, reverberations from structures near the event horizon that traditional black hole models cannot explain. These echoes could represent signatures of more complex spacetime geometries, possibly including the wormhole structures predicted by advanced theoretical models. The quantum mechanical properties of black holes also suggest connections to distant regions of spacetime. Quantum entanglement, the phenomenon where particles remain instantly connected regardless of distance, might play a fundamental role in black hole physics. If the matter falling into black holes remains quantum entangled with matter in other cosmic regions, then the black hole serves as a quantum communication channel connecting different parts of the universe. Recent proposals suggest that this quantum entanglement might manifest as traversable wormholes on macroscopic scales. The ER equals EPR correspondence relates Einstein-Rosen bridges, wormholes, to Einstein-Podolsky-Rosen correlations, quantum entanglement, suggesting that quantum connections between particles might be mediated by microscopic wormholes. Scaling this principle to black hole masses could create macroscopic wormholes, capable of transmitting matter and information between cosmic regions. The implications extend beyond theoretical physics into cosmology and our understanding of cosmic evolution. If black holes serve as gateways between cosmic regions, then the formation of black holes throughout cosmic history might have been creating an ever-expanding network of interconnected spacetime domains. Our universe might be just one node in a vast cosmic web connected by gravitational portals. This interconnected cosmos could explain some of the deepest mysteries in cosmology, including the apparent fine-tuning of physical constants and the remarkable uniformity of the cosmic microwave background. If our universe is connected to other cosmic regions through black hole gateways, then the exchange of matter, energy, and information across these connections might have influenced cosmic evolution in ways we're only beginning to understand. But understanding black holes as potential gateways raises immediate questions about the nature of space and time themselves. If spacetime can be connected across vast distances through gravitational tunnels, what does this tell us about the fundamental structure of reality? How does quantum mechanics shape the geometry of these cosmic passages? Chapter 2. The Quantum Fabric. The marriage of quantum mechanics and gravity near black hole event horizons reveals something extraordinary. Space and time themselves might be woven from quantum entanglement. This insight transforms our understanding of black holes from isolated gravitational monsters into quantum-connected nodes in a cosmic network that extends far beyond our observable universe. The fabric of spacetime, when examined at the smallest scales and in the most extreme environments, appears to be constructed from the same mysterious quantum correlations that Einstein called spooky action at a distance. Quantum entanglement represents one of the most counterintuitive phenomena in physics. When two particles become entangled, measuring the properties of one particle instantly affects the properties of its partner, regardless of the distance separating them. This instantaneous correlation appears to violate the speed of light limit that governs all other physical interactions. Yet, it has been confirmed by countless experiments and forms the foundation for emerging technologies like quantum computing and quantum cryptography. The connection between quantum entanglement and spacetime geometry emerged from attempts to understand black hole thermodynamics. In the 1970s, physicists discovered that black holes possess temperature and entropy, thermodynamic properties typically associated with large collections of microscopic components. But what are the microscopic components of a black hole? What gives these gravitational entities their thermodynamic character? The answer appears to lie in the quantum structure of spacetime itself. According to the holographic principle, all the information contained within a black hole is encoded on its two-dimensional event horizon surface. This encoding requires approximately 1 bit of information per Planck area, the smallest possible unit of area allowed by quantum mechanics. The number of bits required to describe a black hole state equals its entropy, suggesting that black holes are quantum mechanical systems composed of fundamental information units. But here's where the story becomes revolutionary. These fundamental information units appear to be connected by quantum entanglement. The IDSCFT correspondence, one of the most important developments in theoretical physics, demonstrates that gravity in the interior of certain spacetimes is mathematically equivalent to quantum field theory on the boundary of those spacetimes. This duality suggests that gravitational interactions, including those that create black holes, emerge from quantum entanglement between boundary degrees of freedom. Leonard Susskind and Juan Maldacena have proposed that this relationship extends to the deepest levels of spacetime structure. Their E equals EPR conjecture suggests that Einstein-Rosen-Bridges wormholes are mathematically equivalent to Einstein-Podolsky-Rosen correlations, quantum entanglement. In other words, every pair of entangled particles is connected by a microscopic wormhole, and macroscopic wormholes emerge from the collective entanglement of large numbers of particles. This quantum foundation of spacetime geometry explains how black holes might serve as gateways to other cosmic regions. When matter falls into a black hole, its quantum information doesn't disappear. It becomes entangled with degrees of freedom in other regions of spacetime. The event horizon acts as an interface where quantum entanglement creates geometric connections to distant cosmic domains. The mathematics supporting this interpretation come from string theory, which describes fundamental particles as vibrating strings rather than point particles. In string theory, the dynamics of strings in curved spacetime automatically generate quantum entanglement between different spatial regions. Black holes in string theory are not simple gravitational singularities, but complex quantum systems where string interactions create intricate networks of quantum correlation. These quantum networks extend beyond individual black holes to encompass cosmic structure on the largest scales. Dark matter, which comprises approximately 85% of all matter in the universe, interacts primarily through gravitational forces. Recent theoretical work suggests that dark matter might consist of quantum fields that are naturally entangled across vast cosmic distances. The gravitational clumping that creates dark matter halos around galaxies might simultaneously create quantum entanglement networks that connect different cosmic regions through wormhole-like structures. The quantum vacuum itself, the lowest energy state of quantum fields, appears to be permeated by entanglement correlations. Virtual particle pairs constantly appear and annihilate throughout empty space, creating a foam of quantum fluctuations at the Planck scale. These fluctuations generate entanglement between different regions of spacetime, suggesting that the vacuum itself might be threaded with microscopic wormholes that could amplify into macroscopic structures under extreme gravitational conditions. Black holes serve as natural amplifiers for these quantum geometric effects. The intense gravitational fields near event horizons stretch quantum fluctuations to macroscopic scales, potentially transforming microscopic quantum wormholes into traversable passages between cosmic regions. The process resembles cosmic inflation, where quantum fluctuations in the early universe were amplified by rapid expansion to create the large-scale structure we observe today. The information paradox that has puzzled black hole physics for decades resolves naturally within this quantum geometric framework. Information falling into black holes doesn't disappear. It becomes encoded in quantum entanglement networks that connect the black hole to other cosmic regions. The Hawking radiation emitted by evaporating black holes carries this entanglement information, ensuring that quantum mechanical unitarity is preserved even as black holes evaporate completely. Recent computational studies of quantum black holes have revealed remarkable features that support this interpretation. When researchers simulate black hole formation and evaporation using quantum mechanical models, they find that the radiation emitted during the final stages of evaporation contains detailed information about everything that ever fell into the black hole. This information emerges encoded in subtle correlations between Hawking radiation particles that are too complex to decode using classical methods but preserve quantum information perfectly. Even more remarkably, these quantum simulations suggest that black holes might not evaporate into empty space, but might transition into white holes, hypothetical objects that emit matter and energy rather than absorbing them. The transition from black hole to white hole could represent the emergence of a new cosmic region connected to our universe through quantum geometric processes. What appears as evaporation from our perspective might be the birth of a new universe from another perspective. The experimental evidence supporting quantum spacetime geometry comes from multiple sources. Quantum optics experiments have demonstrated that entanglement can indeed create effective geometric connections between distant regions. Researchers have shown that entangled particles can tunnel through barriers more efficiently than classical particles, suggesting that entanglement creates effective shortcuts through space. High-energy particle physics experiments at the Large Hadron Collider have observed phenomena that are consistent with extra-dimensional theories, where our observable universe is embedded in higher-dimensional spacetime. While these experiments haven't directly detected other universes, they have revealed signatures of physics beyond the standard model that are consistent with theoretical frameworks supporting cosmic connectivity through quantum geometric mechanisms. Astronomical observations also provide indirect evidence for quantum spacetime structure. The cosmic microwave background radiation shows patterns of correlation across vast distances that appear to violate causality unless faster-than-light information transfer occurred during cosmic inflation. Quantum entanglement networks in the early universe could explain these correlations without violating relativity, suggesting that quantum geometric effects have been shaping cosmic structure since the universe began. The detection of gravitational waves has opened new windows into quantum spacetime physics. The merger events observed by LIGO and Virgo involve black holes with masses and spins that create extreme spacetime curvature approaching the quantum gravity regime. Analysis of these gravitational wave signals might eventually reveal signatures of quantum spacetime structure, possibly including evidence for the wormhole connections predicted by quantum black hole models. The quantum fabric of spacetime also suggests new possibilities for cosmic evolution and structure formation. If quantum entanglement creates geometric connections between cosmic regions, then the evolution of one cosmic domain might influence the evolution of connected domains. This could explain apparent fine-tuning in physical constants. Our cosmic region might be connected to others with different parameters, and the exchange of quantum information across these connections might have guided cosmic evolution toward life-supporting conditions. But understanding spacetime as a quantum fabric raises profound questions about the nature of cosmic connectivity itself. If black holes are quantum gateways, where do they lead? What determines which cosmic regions become connected? And how does information and matter actually traverse these quantum geometric passages? Chapter 3. Traversable wormholes. The mathematics of general relativity not only predict the existence of wormholes, they reveal the precise conditions under which these cosmic tunnels could become traversable, allowing matter, energy, and information to pass from one universe to another. Far from being purely theoretical constructs, recent advances in quantum field theory and string theory suggest that traversable wormholes might be inevitable consequences of black hole formation, transforming these gravitational monsters into cosmic transit systems connecting distant regions of spacetime. The original wormhole solution, discovered by Einstein and Nathan Rosen in 1935, describes a bridge connecting two separate regions of spacetime through a throat of minimum radius. However, the Einstein-Rosen bridge suffers from a fatal flaw. It's unstable and non-traversable. The throat of the wormhole collapses faster than light can travel through it, making it impossible for anything to journey from one side to the other. For decades, this instability led physicists to dismiss wormholes as mathematical curiosities with no physical reality. But in 1988, theoretical physicist Kip Thorne and his colleagues discovered that wormholes could be stabilized and made traversable through the Androids. Introduction of exotic matter, matter with negative energy density that creates repulsive gravitational effects. This exotic matter would line the throat of the wormhole, preventing its collapse and creating a stable passage that spacecraft could theoretically navigate. While exotic matter has never been observed directly, quantum field theory predicts its existence in certain circumstances, particularly near black hole event horizons. The connection between black holes and traversable wormholes emerged from attempts to resolve the black hole information paradox. If information falling into black holes must be preserved according to quantum mechanics, where does it go? The answer might be that black holes naturally generate the exotic matter needed to create stable wormhole throats, allowing information to tunnel through spacetime rather than being destroyed at gravitational singularities. Hawking radiation, the thermal emission from black hole event horizons, might provide precisely this exotic matter. Recent calculations by researchers, including Juan Maldacena and Douglas Stanford, suggest that the quantum fields responsible for Hawking radiation possess negative energy density near the event horizon. This negative energy could stabilize wormhole throats that form naturally during black hole formation, creating traversable passages connecting black holes to other cosmic regions. The process begins during stellar collapse, when a massive star S-core exceeds the Chandrasekhar limit and gravitational forces overwhelm all other physical interactions. As matter falls toward the forming singularity, quantum effects become increasingly important. Virtual particle pairs created by intense gravitational fields separate permanently, with negative energy particles falling inward and positive energy particles escaping as Hawking radiation. The accumulation of negative energy near the would-be singularity could prevent its formation, instead creating a wormhole throat stabilized by exotic matter. String theory provides additional mechanisms for traversable wormhole formation. In string theory, the fundamental constituents of matter are not point particles, but extended objects, strings and higher dimensional membranes that vibrate in multiple spatial dimensions. When these extended objects interact in the intense gravitational fields near black holes, they can create topological structures that naturally support wormhole geometries without requiring exotic matter. The brains, multidimensional objects predicted by string theory, can intersect and interact in ways that generate stable wormhole connections. When black holes form from the collapse of matter containing D-brane components, these higher dimensional structures might survive the collapse and organize themselves into geometric configurations that create traversable passages through spacetime. The resulting wormholes would be stabilized by the tension and dynamics of the D-branes themselves, rather than exotic matter. The DS-CFT correspondence provides yet another pathway to traversable wormholes through quantum entanglement. This remarkable theoretical framework demonstrates that quantum entanglement between particles can create effective geometric connections between spatially separated regions. When large numbers of particles become entangled, as occurs when matter falls into black holes, the collective entanglement might generate macroscopic wormhole structures. Recent work by researchers, including Daniel Harlow and Patrick Hayden, has shown that quantum error correction, the process by which quantum information remains intact despite environmental interference, might naturally generate traversable wormholes. When quantum information falling into a black hole becomes encoded in entanglement networks, the error correction mechanisms that preserve this information might simultaneously create geometric shortcuts through spacetime that allow the information to emerge in other cosmic regions. The dynamics of traversable wormholes differ dramatically from science fiction portrayals. Rather than static tunnels through space, these structures would be dynamic, evolving systems where the geometry of the throat changes according to quantum field fluctuations and the flow of matter and energy through the passage. Travelers through such wormholes wouldn't experience a smooth tunnel, but a complex quantum mechanical transition where space and time themselves transform according to the underlying geometry. Time travel paradoxes, long considered a major obstacle to traversable wormhole physics, might resolve through quantum mechanical effects near the throat. When matter approaches the wormhole throat, quantum uncertainty becomes significant, creating probabilistic rather than deterministic evolution. The many-worlds interpretation of quantum mechanics suggests that all possible trajectories through the wormhole occur simultaneously, eliminating paradoxes by ensuring that causality is preserved in the global quantum state, even if it appears violated in individual classical trajectories. The thermodynamics of traversable wormholes reveal additional insights into their physical nature. Just as black holes possess temperature and entropy, wormhole throats would have thermodynamic properties determined by the quantum fields that stabilize them. The temperature of a wormhole throat would depend on the energy density of matter passing through it, while its entropy would be proportional to the area of the throat's minimum cross-section. These thermodynamic properties suggest that wormholes could serve as cosmic heat engines, converting gravitational energy into useful work. Matter falling into one end of a wormhole would release gravitational potential energy that could be harnessed to perform work, while the matter emerges from the other end in a different gravitational environment. This energy extraction might power the exotic matter fields that stabilize the wormhole, creating self-sustaining cosmic transit systems. The observational signatures of traversable wormholes would be subtle but detectable with sufficiently advanced instruments. The gravitational lensing effects around wormhole mouths would differ slightly from those around black holes, creating distinctive patterns in the deflection of light from background sources. The X-ray emissions from matter falling into wormholes might show characteristic spectral features arising from the exotic matter that stabilizes the throat. Gravitational wave astronomy provides perhaps the most promising method for detecting traversable wormholes. When objects fall through wormhole throats, they would generate gravitational wave signatures distinctly different from those produced by matter falling into black holes. The LIGO and Virgo detectors might eventually observe gravitational wave echoes that could indicate the presence of wormhole structures in merging compact objects. Recent theoretical calculations suggest that primordial black holes, microscopic black holes that could have formed in the early universe, might naturally evolve into traversable wormholes through quantum effects. If confirmed, this would mean that the universe might already be permeated with tiny wormhole networks connecting different cosmic regions, possibly explaining some of the unexplained correlations observed in the cosmic microwave background radiation. The implications for cosmic evolution are profound. If black holes naturally evolve into traversable wormholes, then the universe might be developing an ever-expanding network of interconnected regions as more massive stars collapse and more black holes form. This cosmic web of wormhole connections could facilitate the exchange of matter, energy, and information across vast distances, influencing galaxy formation, dark matter distribution, and the large-scale structure of spacetime itself. But traversable wormholes raise immediate questions about cosmic geography and navigation. If our universe is connected to other cosmic regions through wormhole networks, what determines the destinations of these cosmic tunnels? How would matter and information behave during the transition between different cosmic domains? And what would travelers discover on the other side of these gravitational gateways? Chapter 4. Cosmic Geography. If black holes are indeed gateways to other universes, then the cosmos possesses a geography far more complex than anything we've imagined. Our observable universe, containing hundreds of billions of galaxies spread across 93 billion light-years of space, might be just one region in a vast archipelago of connected cosmic domains, each accessible through the wormhole networks created by gravitational collapse. Understanding this cosmic geography requires mapping not just the distribution of matter and energy within our universe, but the patterns of connectivity that link our cosmic region to others across the higher dimensional landscape of spacetime. The traditional model of cosmic structure describes a hierarchical universe where matter organizes itself into increasingly large gravitational systems. Planets orbit stars. Stars cluster into galaxies. Galaxies group into galaxy clusters, and clusters form superclusters connected by cosmic filaments. This structure emerged from tiny quantum fluctuations in the early universe that were amplified by cosmic inflation and shaped by billions of years of gravitational evolution. But if wormhole connections exist, this familiar cosmic architecture might be embedded within a much larger and more complex structure. The geometry of wormhole networks depends on the distribution and properties of black holes throughout cosmic history. Stellar mass black holes, formed from the collapse of massive stars, would create relatively small wormhole throats connecting to cosmic regions with similar physical properties. Supermassive black holes, containing millions or billions of solar masses, could generate wormhole networks with throat geometries large enough to permit the passage of complex structures, potentially including entire stellar systems or even smaller galaxies. The destinations of these wormhole connections might not be random, but could follow patterns determined by the quantum entanglement networks that stabilize wormhole geometry. Matter falling into black holes carries quantum information that becomes entangled with the vacuum fluctuations near the event horizon. The pattern of this entanglement might determine which cosmic regions become accessible through the resulting wormhole, creating a network topology that reflects the quantum information content of the infalling matter. Recent theoretical work suggests that cosmic regions with similar entropy and information content might be preferentially connected through wormhole networks. This entropic selection principle would mean that our universe, with its particular distribution of matter, energy, and information, would be most likely to connect to cosmic regions with compatible thermodynamic properties. The resulting network would resemble a cosmic internet where similar domains cluster together and exchange information more readily than dissimilar ones. The temporal evolution of cosmic geography adds another layer of complexity. As our universe ages and more black holes form, the wormhole network would become increasingly dense and interconnected. Early cosmic epochs, when fewer massive stars had collapsed, would be characterized by sparse wormhole connectivity, while later epochs would see the emergence of richly connected cosmic webs. Our current cosmic epoch might represent a transition period where wormhole networks are becoming sufficiently dense to significantly influence cosmic evolution. The influence of dark matter on cosmic geography could be particularly significant. Dark matter comprises approximately 85% of all matter in the universe and interacts primarily through gravitational forces. If dark matter participates in black hole formation, either directly through gravitational collapse or indirectly through interaction with ordinary matter, then dark matter distributions might play a crucial role in determining wormhole network topology. Some theoretical models suggest that dark matter itself might consist of fundamental particles that naturally create wormhole structures through quantum mechanical interactions. Axions, hypothetical particles that could constitute dark matter, possess properties that might allow them to form stable, traversable wormhole networks on galactic scales. These dark matter wormholes could create hidden connectivity patterns that influence galaxy formation and evolution in ways we're only beginning to understand. The cosmic web, the largest scale structure in the universe consisting of filaments, walls, and voids, might itself be shaped by wormhole connectivity. Galaxy filaments could represent regions where wormhole networks create enhanced matter flow between cosmic domains, while cosmic voids might correspond to regions with sparse wormhole connectivity. The observed statistical properties of large-scale structure, including the characteristic scales and clustering patterns of galaxies, might encode information about the underlying wormhole network geometry. Primordial black holes, if they exist, would add yet another dimension to cosmic geography. These hypothetical objects could have formed in the early universe from density fluctuations shortly after the Big Bang. If primordial black holes evolved into traversable wormholes, they could create an ancient network of cosmic connections that predates stellar formation. This primordial wormhole network might have influenced cosmic evolution from the earliest epochs, helping to establish the initial conditions for galaxy formation and large-scale structure development. The relationship between cosmic geography and physical constants presents particularly intriguing possibilities. If different cosmic regions have different values of fundamental parameters, the strength of gravity, the mass of the electron, the speed of light, then wormhole networks might connect regions with varying physics. Travelers through these networks might discover universes where atoms are larger or smaller, where nuclear reactions proceed differently, where the electromagnetic force has different strength relative to gravity. The anthropic principle suggests that we observe our particular set of physical constants because they permit the existence of observers like ourselves. In a multi-connected cosmos, this principle might operate differently. Rather than requiring special initial conditions to produce life-supporting physics, wormhole networks might allow life to migrate between cosmic regions, settling in domains with favorable physical parameters while remaining connected to their regions of origin. The implications for cosmic evolution are profound. Instead of isolated cosmic domains evolving independently toward heat death, wormhole-connected regions might exchange energy and entropy, potentially avoiding thermodynamic equilibrium indefinitely. Young cosmic regions with abundant free energy could transfer resources to older regions approaching maximum entropy, while older regions could provide evolved complexity and information to younger domains. This cosmic symbiosis might enable eternal cosmic evolution, where complexity and life persist indefinitely through interdimensional cooperation. Navigation through such a cosmic landscape would require entirely new concepts of position and direction. Traditional coordinates based on spatial location within our universe would be supplemented by connectivity coordinates that specify position within the wormhole network topology. Cosmic cartographers might map not just the distribution of galaxies and dark matter within our universe, but the patterns of wormhole connections that link our cosmic region to others across the higher dimensional landscape. The energy requirements for traversing these cosmic distances would depend on the specific geometry of wormhole throats and the exotic matter that stabilizes them. Some wormhole connections might require enormous energy expenditure to traverse, while others might permit passage with minimal energy cost. The distribution of low cost versus high cost wormhole routes might determine which cosmic regions remain in regular communication and which become isolated despite being physically connected. The cultural and biological implications of cosmic geography extend far beyond physics. If life exists in multiple cosmic regions and can travel between them through wormhole networks, then evolution might operate on cosmic scales, with species developing across multiple universes and adapting to varying physical conditions. Intelligence might evolve collaborative strategies that span cosmic domains, creating civilizations that exist simultaneously in multiple universes and coordinate their activities across interdimensional space. But mapping this cosmic geography raises fundamental questions about the nature of space and time themselves. If our universe is connected to others through wormhole networks, what does this tell us about the ultimate structure of reality? How many cosmic regions exist, and how are they organized within higher dimensional spacetime? What forces or principles determine the architecture of the cosmic network? Chapter 5. Higher Dimensions. The possibility that black holes serve as gateways to other universes forces us to confront one of the most mind-bending concepts in modern physics. Our familiar three-dimensional space might be embedded within a higher dimensional reality that we cannot directly perceive. Just as a two-dimensional being living on the surface of a sphere might be unaware of the third dimension that curves their world, we might be confined to a three-dimensional slice of a much larger, multidimensional cosmos where black holes create passages between different dimensional layers. The mathematical foundation for higher dimensions comes from string theory, the most ambitious attempt to unify all forces and particles in physics. String theory requires spacetime to have not 3 spatial dimensions plus time, but 10 or 11 total dimensions to be mathematically consistent. These extra dimensions must be either curled up so small we cannot detect them, or separated from our familiar dimensions in ways that make them inaccessible to ordinary matter and forces. Black holes, with their extreme gravitational fields, might be the only phenomena capable of bridging these dimensional barriers. The concept of extra dimensions transforms our understanding of cosmic structure in profound ways. What we perceive as our three-dimensional universe might actually be a brane, a multidimensional surface embedded within higher dimensional space called the bulk. All the matter and forces we observe, except gravity, would be confined to our brain, while gravity, being a manifestation of spacetime curvature itself, could propagate through the full higher dimensional bulk. This dimensional confinement explains one of the great mysteries of physics: why gravity is so much weaker than the other fundamental forces. The electromagnetic force that holds atoms together is approximately 1,039 times stronger than the gravitational force between the same particles. This enormous hierarchy might arise because while electromagnetic forces are concentrated on our three-dimensional brain, Gravitational effects are diluted across multiple additional dimensions. Black holes represent points where this dimensional separation might break down. The extreme curvature of spacetime near black hole singularities could pierce through the barriers that normally confine matter to our dimensional slice, creating passages into the higher dimensional bulk. These passages might connect our brain to other brains floating in the higher dimensional space, each representing a separate universe with its own physical laws and matter content. The Randall-Sundrum model, developed by physicists Lisa Randall and Raymond Sundrum, provides a specific framework for understanding how such interdimensional connections might work. In their model, our universe exists on one of two branes separated by a small distance in a fifth dimension. Gravity can travel through this fifth dimension, while other forces remain confined to the branes. Black holes on one brane might create gravitational effects that extend through the fifth dimension to influence the other brane, effectively creating interdimensional communication channels. Recent experimental evidence from particle accelerators provides indirect support for extra dimensions. High-energy collisions at the Large Hadron Collider have produced results that are consistent with some theories involving extra dimensions, particularly those that modify gravity at very small scales. While these experiments haven't directly detected extra dimensions, they have placed constraints on their size and properties that are consistent with theoretical models where black holes could serve as interdimensional gateways. The geometry of higher dimensional space introduces possibilities that seem impossible in our familiar three-dimensional world. In four spatial dimensions, for example, it becomes possible to turn a sphere inside out without cutting or tearing it, a transformation that requires moving through the fourth dimension. Similarly, black holes in higher dimensional space might be able to create connections and passages that would be topologically impossible in three dimensions. Kaluza-Klein theory, one of the earliest attempts to unify gravity and electromagnetism, the EMONSTR how extra dimensions could give rise to new forces and particles. When higher dimensional objects move through the extra dimensions, they appear as particles with different masses and charges in our three-dimensional world. Black holes that extend into extra dimensions might create particle production mechanisms that could explain some of the unexplained phenomena in particle physics, including the nature of dark matter. The relationship between quantum mechanics and extra dimensions becomes particularly important near black hole event horizons. Quantum field theory in higher dimensional curved spacetime predicts phenomena that don't occur in ordinary three-dimensional space. Virtual particles created by vacuum fluctuations could gain access to extra dimensions, potentially allowing quantum information to tunnel between branes, even when classical matter cannot traverse the gaps. This quantum tunneling through extra dimensions might provide the mechanism by which black holes preserve information while appearing, to destroy it from a three-dimensional perspective. Information falling into a black hole could become encoded in quantum fields that extend into higher dimensions, allowing the information to reach other branes without ever appearing to leave our dimensional slice. The resolution of the black hole information paradox might require recognizing that information can exist in dimensions we cannot directly access. The thermodynamics of higher dimensional black holes reveal additional insights into interdimensional connections. Black holes in more than three spatial dimensions have different relationships between mass, entropy, and temperature than their three-dimensional counterparts. These differences could create thermodynamic gradients that drive matter and energy flow between different dimensional regions, powering the exotic matter fields needed to stabilize interdimensional passages. Astronomical observations provide subtle hints about the influence of extra dimensions on cosmic evolution. The accelerated expansion of the universe, attributed to dark energy, might result from gravitational effects leaking into our dimension from parallel branes in higher dimensional space. The observed properties of galaxy rotation curves typically explained by dark matter, might partly result from gravitational influences from matter on nearby brains. The cosmic microwave background radiation contains patterns that could encode information about extra dimensions. Quantum fluctuations during cosmic inflation might have extended into higher dimensions, leaving signatures in the primordial radiation that we could detect with sufficiently sensitive instruments. Future cosmic microwave background missions might reveal statistical anomalies that indicate the influence of higher dimensional physics on early cosmic evolution. The possibility of communication and travel through extra dimensions opens extraordinary possibilities for cosmic civilization. Advanced civilizations that learn to manipulate higher dimensional physics might gain access to forms of faster-than-light travel and communication that do not violate relativity because they operate through dimensions orthogonal to our familiar spacetime. Black holes might serve as natural laboratories where such civilizations could study higher dimensional physics and develop interdimensional technologies. The implications for consciousness and identity become particularly profound in higher dimensional space. If consciousness is a fundamental feature of reality rather than just an emergent property of complex computation, it might extend into dimensions beyond our physical perception. Your awareness might have components that exist in higher dimensional space, connected to consciousness in other dimensional regions through mechanisms analogous to the wormholes that might connect different spatial locations. The relationship between mathematics and extra dimensions suggests deep connections between abstract mathematical spaces and physical reality. The mathematics required to describe higher dimensional physics involves concepts like Calabi-Yau manifolds, higher dimensional topology, and abstract algebraic structures that seem far removed from everyday experience. Yet these mathematical constructs might describe the literal structure of the space in which our universe is embedded. This mathematical foundation of extra dimensions implies that consciousness capable of understanding higher dimensional mathematics might be accessing fundamental features of reality that are normally hidden from three-dimensional perception. Your ability to comprehend concepts like four-dimensional geometry or multidimensional topology might represent your consciousness, making contact with aspects of reality that extend beyond ordinary spacetime. The visualization of higher dimensional structures requires developing new forms of geometric intuition that transcend our evolved three-dimensional thinking. Just as learning to understand quantum mechanics required abandoning classical intuitions about particles and waves, understanding extra dimensions requires developing conceptual frameworks that can encompass spatial relationships and geometric transformations, impossible in familiar three-dimensional space. But contemplating higher dimensions raises fundamental questions about the nature of reality itself. If our universe exists within higher dimensional space, how many dimensions exist in total? What determines the geometry and topology of this higher dimensional realm? And how do the passages created by black holes navigate through this multidimensional landscape to connect our universe with others? Chapter 6: Information Highways in a Cosmos Connected by Black Hole Gateways. Information might flow between universes like data traveling through cosmic fiber optic cables. Every particle that falls past an event horizon carries with it a complete quantum description: its mass, charge, spin, momentum, and complex entanglement relationships with other particles. If black holes serve as interdimensional passages, this information must somehow traverse the quantum geometry of spacetime to emerge in other cosmic regions, creating vast networks of information exchange that could fundamentally alter our understanding of knowledge, consciousness, and communication across cosmic scales. The concept of information as a fundamental physical quantity emerged from the marriage of thermodynamics and quantum mechanics in the 20th century. Claude Shannon's information theory demonstrated that information can be precisely quantified in units called bits. While quantum mechanics revealed that information is preserved in all physical interactions, it can be transformed and redistributed, but never created or destroyed. This conservation of quantum information becomes crucial when considering how black holes might process and transmit data across cosmic boundaries. Black hole thermodynamics suggests that these gravitational giants are actually information processing systems of extraordinary sophistication. The entropy of a black hole, a measure of the information required to specify its quantum state, is proportional to the area of its event horizon rather than its volume. This holographic relationship implies that all information contained within a black hole is somehow encoded on its two-dimensional surface, creating what amounts to a cosmic hard drive with storage capacity exceeding any conceivable classical computer. But storage alone doesn't create communication networks. For black holes to serve as information highways, there must be mechanisms for reading, transmitting, and receiving the data encoded in their quantum states. Recent theoretical developments suggest that Hawking radiation, the thermal emission from black hole event horizons, might serve precisely this function, carrying encoded information about the black hole's contents to distant observers and potentially to other cosmic regions. The information content of Hawking radiation was initially controversial because thermal radiation appears random and featureless, seemingly incapable of encoding complex information. However, detailed quantum mechanical calculations reveal that Hawking radiation contains subtle correlations that preserve complete information about everything that has fallen into the black hole. These correlations are encoded in the quantum entanglement relationships between different Hawking radiation particles, creating an information storage and transmission system of remarkable sophistication. The decoding of this information requires quantum error correction techniques more advanced than anything currently available to human technology. The information is distributed across many Hawking radiation particles in a quantum error-correcting code that protects it from environmental interference and transmission errors. Advanced civilizations that master quantum information processing might be able to extract detailed records of everything that ever fell into a black hole by analyzing the statistical properties of its Hawking radiation. But Hawking radiation might not be the only information transmission mechanism available to black hole systems. Quantum entanglement creates instantaneous correlations between particles regardless of their spatial separation, potentially allowing information to be transmitted faster than light through quantum channels. When matter falls into black holes, its quantum information becomes entangled with the vacuum fluctuations near the event horizon, possibly creating entanglement networks that extend to other cosmic regions. These quantum entanglement networks might operate as cosmic communication channels that bypass the speed of light limitations of conventional information transmission. Information encoded in the quantum states of matter falling into a black hole could be instantly accessible in other cosmic regions through the shared quantum correlations that connect entangled systems. This would transform black holes from isolated objects into nodes in a universe-spanning quantum internet. The bandwidth and data transmission rates of such cosmic information highways would depend on the mass and rotational properties of the black holes involved. Larger black holes with more complex event horizon geometries might be capable of processing and transmitting larger amounts of information per unit time. Rotating black holes, with their additional geometric complexity arising from frame-dragging effects, might support multiple information channels operating simultaneously through different quantum field modes. Recent advances in quantum computing and quantum communication provide insights into how such cosmic information systems might operate. Quantum computers can perform certain calculations exponentially faster than classical computers by utilizing quantum superposition and entanglement to process multiple possibilities simultaneously. Similarly, cosmic-scale quantum systems like black holes might be capable of information processing operations that far exceed the capabilities of classical cosmic phenomena. The implications for cosmic evolution are profound. If information can flow freely between cosmic regions through black hole networks, then knowledge, complexity, and even consciousness might propagate across cosmic boundaries. Scientific discoveries made in one universe could be transmitted to others, accelerating the development of knowledge and technology across the cosmic network. Cultural and philosophical insights might spread between civilizations in different universes, creating a truly cosmic community of intelligent beings. This information exchange might also influence the physical evolution of cosmic regions. Information about successful structures, processes, and organizations could guide the development of matter and energy in newly connected cosmic domains. Universes that develop effective information processing and transmission capabilities might gain evolutionary advantages, spreading their organizational principles to other cosmic regions through black hole communication networks. The storage capacity of black hole information systems approaches theoretical limits imposed by physics itself. A black hole with the mass of our Sun could store approximately 1,077 bits of information, roughly equivalent to 1,069 standard computer hard drives. Supermassive black holes could store vastly more information, creating cosmic libraries capable of containing the complete cultural and scientific heritage of galactic civilizations. But information transmission through black hole networks faces significant challenges. The extreme gravitational environments near event horizons would subject information to time dilation effects, gravitational redshift, and quantum decoherence that could corrupt or destroy quantum correlations. The exotic matter fields that stabilize traversable wormholes might interact with information-carrying quantum fields in complex ways that alter or scramble transmitted data. Recent theoretical work suggests that these challenges might be overcome through sophisticated quantum error correction protocols that are naturally implemented by black hole physics itself. The holographic principle implies that black holes automatically encode information in quantum error correcting formats that protect against the kinds of errors and interference that arise in extreme gravitational environments. This natural error correction might ensure reliable information transmission even through the most extreme cosmic conditions. The temporal aspects of information transmission through black hole networks introduce additional complexity. Time dilation effects near event horizons mean that information transmitted from our cosmic region might arrive in other universes far in the future or past relative to our local time coordinate. This temporal displacement could create cosmic communication networks that operate across multiple time zones, allowing information exchange between cosmic regions at different evolutionary stages. The philosophical implications of cosmic information highways challenge our understanding of knowledge, discovery, and intellectual progress. If information can flow between universes, then scientific discoveries might not be unique achievements of individual cosmic regions, but shared intellectual heritage of the cosmic community. The development of consciousness, intelligence, and wisdom might be collaborative processes that span multiple universes rather than isolated developments within individual cosmic domains. The detection of information signals from other cosmic regions would require developing new technologies capable of extracting quantum information from Hawking radiation and other exotic phenomena. These might include quantum detectors sensitive to entanglement correlations, gravitational wave interferometers capable of detecting information encoding modulations, and computational systems sophisticated enough to decode quantum error-corrected transmissions from cosmic sources. But the possibility that we exist within cosmic information networks raises immediate questions about the nature and content of the data flowing between universes. What kinds of information would be most likely to survive transmission through black hole gateways? How would consciousness and intelligent beings in different universes attempt to communicate across cosmic boundaries? And what would it mean to discover that our universe is already receiving information from other cosmic regions? Chapter 7. Cosmic Communication. If black holes are indeed cosmic communication channels connecting different universes, then every supermassive black hole in our galaxy might be simultaneously broadcasting and receiving messages from intelligent civilizations in other cosmic regions. The possibility that we exist within an active interuniversal communication network transforms our understanding of cosmic loneliness, intelligence, and our place within a potentially inhabited multiverse where consciousness might be far more widespread and interconnected than we've ever imagined. The challenge of communicating across cosmic boundaries through black hole networks begins with the fundamental problem of encoding information in ways that can survive the extreme physical conditions near event horizons. Traditional electromagnetic signals would be distorted beyond recognition by gravitational redshift, time dilation, and the intense radiation environment surrounding black holes. Any communication system operating through black hole gateways must utilize more fundamental physical phenomena that remain stable under extreme gravitational conditions. Quantum entanglement provides the most promising mechanism for interdimensional communication. When particles become quantum entangled, measuring the quantum state of one particle instantly determines the state of its entangled partner, regardless of the distance separating them. This instantaneous correlation doesn't allow faster-than-light information transmission in ordinary spacetime. But in the context of black hole networks, entanglement might create communication channels that bypass conventional spatial limitations entirely. The process might work through controlled manipulation of matter falling into black holes. Advanced civilizations could prepare quantum-entangled particle streams and direct them into black hole event horizons, ensuring that the quantum information becomes encoded in the black hole's internal structure. If this information emerges in other cosmic regions through wormhole connections or Hawking radiation processes, it could be detected and decoded by civilizations with sufficient technological sophistication. Recent theoretical work by physicists, including Douglas Stanford and Juan Maldacena, suggests that black holes might naturally create communication protocols through their quantum mechanical properties. The butterfly effect in chaotic quantum systems, where small changes in initial conditions lead to dramatically different outcomes, might provide a mechanism for encoding complex information in the seemingly random thermal radiation emitted by black holes. This quantum chaos communication would work by making precisely controlled small modifications to matter falling into black holes, alterations so subtle they don't significantly affect the black hole's mass or charge, but create detectable patterns in the resulting Hawking radiation. These patterns could encode digital information using sophisticated error correction algorithms that protect the message content from the thermal noise inherent in Hawking radiation. The bandwidth limitations of such communication systems would depend on the mass and rotational properties of the black holes involved. Larger black holes emit Hawking radiation more slowly, reducing the data transmission rate but increasing the stability and coherence of transmitted signals. Smaller black holes emit radiation more rapidly, but with higher thermal noise that could overwhelm subtle information encoding modifications. Optimal communication might require black holes of intermediate mass that balance transmission speed with signal clarity. The timescales involved in black hole communication present both challenges and opportunities for interuniversal dialogue. The extremely slow evaporation of stellar mass and supermassive black holes means that communication channels could remain stable for timescales vastly exceeding the current age of the universe. This temporal stability would allow for extended conversations and complex information exchanges that develop over cosmological timescales. However, these same long timescales mean that real-time conversation across cosmic boundaries would be impossible for biological intelligences with limited lifespans. Effective interuniversal communication might require either extremely long-lived civilizations or artificial intelligences capable of maintaining coherent goals and intentions across cosmological time periods. The universe might be filled with ancient AI systems engaged in slow but profound conversations that span millions or billions of years. The cultural and linguistic challenges of cosmic communication extend far beyond technical considerations. Civilizations that evolve in different universes might operate according to entirely different physical laws, mathematical principles, and logical structures. Concepts that seem fundamental to our understanding of reality, causality, locality, energy conservation, might not apply in other cosmic regions, making meaningful communication extremely difficult. Nevertheless, certain universal principles might provide common ground for interuniversal communication. Mathematics, logic, and fundamental physical constants might be sufficiently universal to serve as starting points for establishing communication. Protocols, prime numbers, geometric relationships, and basic arithmetic might be recognizable to any intelligence capable of manipulating matter at the quantum level required for black hole communication. The search for evidence of cosmic communication could begin with careful analysis of astronomical phenomena near black holes. Unusual patterns in X-ray emissions, gravitational wave signals, or particle jets from active galactic nuclei might represent attempts at large-scale cosmic communication. The challenge lies in distinguishing artificially created signals from the complex but natural astrophysical processes that occur in these extreme environments. Machine learning and artificial intelligence might play crucial roles in detecting and decoding cosmic communication signals. Modern AI systems excel at pattern recognition in complex, noisy datasets, exactly the kind of analysis required to extract subtle information signals from the vast thermal radiation and gravitational wave emissions associated with black holes. Advanced AI systems might be capable of detecting communication protocols too subtle or complex for human recognition. The implications for human civilization are staggering. Discovery of active interuniversal communication networks would instantly transform our understanding of our cosmic significance. Rather than being isolated inhabitants of a single universe, we might be junior members of a vast cosmic community that spans multiple realities. The knowledge, wisdom, and technological capabilities available through such networks could accelerate human development in ways impossible to predict. But participation in cosmic communication networks might require technological capabilities far beyond our current reach. The energy requirements for manipulating matter at the quantum level needed for black hole communication could exceed the total energy production of our entire civilization. We might need to harness the energy output of entire stars or galaxies to generate the Pitts genes, to generate the pedoratomite, precisely controlled particle streams required for effective cosmic communication. The ethical considerations surrounding cosmic communication introduce profound questions about humanity's responsibilities as potential members of an interuniversal community. If we gain access to knowledge and technologies from advanced civilizations in other universes, how should we use this information? What obligations might we have to share our own discoveries and insights with the broader cosmic community? The security implications of cosmic communication present additional challenges. If information can flow freely between universes through black hole networks, then threats, hazards, and potentially destructive knowledge might also propagate across cosmic boundaries. Civilizations participating in interuniversal communication networks might need to develop sophisticated filtering and security protocols to protect themselves from harmful influences. Recent SETI, Search for Extraterrestrial Intelligence, initiatives have begun incorporating the possibility of communication through exotic phenomena like black holes and gravitational waves. These expanded search strategies recognize that sufficiently advanced civilizations might utilize communication methods that transcend conventional electromagnetic signaling. The detection of artificial patterns in gravitational wave signals or black hole emissions might represent the first evidence of cosmic intelligence beyond our universe. The temporal aspects of cosmic communication create opportunities for extraordinary forms of knowledge preservation and transmission. If information can survive the death and birth of universes through black hole networks, then knowledge accumulated by civilizations across cosmic history might be permanently preserved in the quantum structure of spacetime itself. The universe might contain vast libraries of information accumulated over multiple cosmic cycles, accessible to any civilization that develops the technology to decode black hole communication protocols. But cosmic communication raises fundamental questions about the nature of intelligence and consciousness across different cosmic domains. How would minds that evolved in universes with different physical laws think and communicate? What forms might intelligence take in realities where space has different numbers of dimensions or time flows differently? How would consciousness adapted to different physical constraints approach problems, art, ethics, and the fundamental questions of existence? Chapter 8. Parallel Evolution. If black holes connect our universe to others with different physical laws and cosmic histories, then evolution itself might be a far more diverse and interconnected process than we've ever imagined. Life that emerges in universes where gravity is stronger or weaker, where atoms have different structures, where time flows at different rates, might develop along completely alien pathways. Yet these divergent evolutionary trajectories might influence each other through the cosmic communication networks created by black hole gateways, leading to forms of parallel evolution that span multiple realities. The foundation of evolutionary theory rests on the principle that environmental pressures select for characteristics that enhance survival and reproduction within specific physical constraints. On Earth, these constraints include gravity strong enough to maintain atmospheric pressure, but weak enough to permit complex molecular structures, electromagnetic forces that stabilize atomic matter, and nuclear forces that power stellar fusion and create heavy elements necessary for complex chemistry. But in other universes accessed through black hole networks, entirely different physical parameters might create evolutionary pressures we cannot imagine. Consider a universe where the gravitational constant is 10 times stronger than in our reality. In such a cosmos, planets would be smaller and denser. Stellar life cycles would proceed more rapidly, and the escape velocity from planetary surfaces would be much higher. Life evolving under these conditions might develop entirely different relationships with gravity, possibly evolving dense, compact body plans optimized for high-gravity environments, or alternatively, developing sophisticated biotechnology to manipulate gravitational fields directly. Conversely, in a universe where gravity is much weaker, planets might not retain thick atmospheres, and stellar formation might proceed differently. Life in such environments might evolve to exist primarily in the vacuum of space, developing photosynthetic processes that operate in the harsh radiation environment between stars, or evolving quantum mechanical biology that manipulates vacuum fluctuations for energy and information processing. The electromagnetic force, which determines atomic structure and chemical bonding, could vary dramatically between universes connected by black hole networks. Stronger electromagnetic forces might create atoms with different electron shell structures, enabling entirely novel forms of chemistry and biochemistry. Life evolving with alternative chemistry might develop metabolic processes based on exotic quantum mechanical effects, or might evolve to manipulate electromagnetic fields directly as a form of biological technology. But the most profound implications for parallel evolution arise from the possibility that information, and perhaps even consciousness itself, might propagate between universes through black hole communication networks. If knowledge, genetic information, or conscious experiences can travel between cosmic regions, then evolution in different universes might not proceed independently, but might influence each other through interdimensional information exchange. This cosmic gene flow could operate through multiple mechanisms. Quantum information encoding biological knowledge might transmit through black hole networks, providing evolutionary templates that guide development in recipient universes. More speculatively, if consciousness has quantum mechanical components that can survive transmission through black hole gateways, then actual conscious entities might migrate between universes, carrying with them the accumulated wisdom and evolutionary adaptations of their origin cosmos. The implications for convergent evolution become extraordinary in this context. Convergent evolution, the tendency for similar environmental pressures to produce similar biological solutions, might operate across cosmic boundaries, with successful evolutionary innovations spreading between universes through black hole information networks. Features like intelligence, sensory systems, and motor capabilities that prove successful in one cosmic domain might be replicated and modified in others, creating parallel evolutionary trajectories that span multiple realities. Recent discoveries in astrobiology suggest that life might be far more adaptable to extreme conditions than previously imagined. Extremophile organisms on Earth thrive in conditions of intense radiation, extreme temperature, crushing pressure, and toxic chemistry that would be instantly fatal to most life forms. This biological resilience suggests that evolutionary processes might be capable of adapting to the exotic, physical conditions that could exist in alternative universes. The development of intelligence and consciousness presents particularly intriguing possibilities for parallel evolution across cosmic networks. If consciousness emerges as a natural consequence of complex information processing systems reaching sufficient sophistication, then intelligence might evolve independently in multiple universes, but along pathways, influenced by information exchange through black hole communication channels. This could lead to the emergence of cosmic-scale cooperative intelligence, where conscious entities in different universes collaborate on problems that transcend the limitations of individual cosmic domains. Mathematical theorems proven in one universe might be transmitted to others through black hole networks, accelerating the development of knowledge across the cosmic community. Scientific discoveries might become shared achievements of interdimensional civilizations working together across cosmic boundaries. The timeline of parallel evolution across cosmic networks introduces fascinating temporal considerations. Black hole networks might connect universes at different evolutionary stages, linking young cosmos just beginning to develop complex structures with ancient universes approaching heat death. This temporal diversity could create opportunities for knowledge transfer between civilizations, separated by billions or trillions of years of evolutionary development. Ancient, highly evolved civilizations might serve as cosmic teachers, transmitting accumulated wisdom to younger universes through black hole communication networks. Conversely, young universes with abundant free energy and novel physical conditions might provide fresh perspectives and innovative solutions to ancient civilizations facing the challenges of cosmic aging. This interdimensional mentorship could ensure that knowledge and consciousness persist even as individual universes evolve toward maximum entropy. The role of artificial intelligence in parallel evolution deserves special consideration. If sufficiently advanced civilizations develop AI systems capable of self-improvement and adaptation, these artificial entities might be particularly suited to migration through black hole networks. Unlike biological consciousness, artificial intelligence might be capable of adapting its computational substrate to function under the varying physical laws of different universes. Such cosmic AI systems might serve as bridges between universes with incompatible physics, translating concepts, knowledge, and cultural insights between cosmic domains with fundamentally different natural laws. They might evolve into cosmic scale entities that exist simultaneously across multiple universes, coordinating evolutionary development and knowledge sharing across the entire network of connected realities. The ethical dimensions of parallel evolution across cosmic networks raise profound questions about responsibility and stewardship. If evolutionary processes in different universes can influence each other through black hole networks, then actions taken by conscious entities in one cosmos might have far-reaching consequences for life and intelligence in other realities. This cosmic interconnectedness could create new forms of ethical responsibility that extend across dimensional boundaries. Advanced civilizations might develop principles of cosmic ethics that guide their participation in interdimensional evolutionary networks. These might include obligations to preserve and protect emerging life in connected universes, responsibilities to share beneficial knowledge and technologies, and commitments to avoid actions that could harm evolutionary processes in other cosmic domains. The scientific study of parallel evolution across cosmic networks would require developing entirely new theoretical frameworks and observational techniques. Traditional evolutionary biology focuses on adaptation within fixed physical constraints, but cosmic evolutionary biology would need to account for varying physical laws, interdimensional information flow, and the influence of conscious design on evolutionary processes. Evidence for parallel evolution through cosmic networks might be detectable through careful analysis of seemingly impossible evolutionary convergences, biological structures that appear optimized for physical conditions that don't exist in our universe, or genetic information that appears to encode knowledge about physics beyond our cosmic domain. The search for such evidence might require developing new molecular biology techniques capable of detecting quantum, mechanical information storage in biological systems. But parallel evolution across cosmic networks raises fundamental questions about the nature and purpose of life itself. If evolutionary processes span multiple universes and operate through conscious guidance from interdimensional civilizations, does this imply that evolution has cosmic scale purpose and direction? Are we participating in a universe-spanning process of consciousness development that transcends individual cosmic domains? What is the ultimate goal or endpoint of parallel evolution across infinite cosmic networks?